Welcome to The Explainer. I am absolutely thrilled to have you here today. We're tackling one of the most exciting, yet honestly, notoriously frustrating challenges in AI engineering right now. And that is moving Retrieval Augmented Generation, or RAG, from a fragile little local script that works perfectly on your laptop to a robust, bulletproof production app. I mean, imagine you're building an internal HR bot to answer employee policy questions, or maybe a customer-facing app for a bank. You build a quick prototype, it works flawlessly with a few test PDFs, and you feel like an absolute genius. But the second you connect it to real-world, messy, massive company data, the whole system just crumbles. If you've ever experienced that exact heartbreak, you are in the exact right place.
Okay, let's dive right into this, because 90% of RAG systems fail in production. 90%. That is a staggering statistic. And you know what the really crazy part is? They all fail for the exact same reasons. It's incredibly frustrating for developers to spend weeks fine-tuning an application only to watch it just completely hallucinate answers to users, simply because the underlying architecture wasn't built to scale. So today, we're going to unpack exactly what those failure reasons are, and more importantly, how you can actually engineer your way past them. We are not just building a toy application today, we are building for true enterprise scale.
Here is the builder's journey we're taking today. We'll start with 1, the RAG concept explained, then move into 2, core architecture, and 3, local setup. After that, we'll hit 4, the production cliff, explore 5, advanced architectures, and finally tackle 6, RAG versus long context.
Let's kick things off with Section 1, the RAG concept explained.
A great way to think about retrieval augmented generation is using the doctor analogy. Basically, a large language model is like a brilliant world-class doctor who has read literally every medical textbook ever written. But when a new patient walks in, that doctor still absolutely needs their specific, up-to-date medical reports to give an accurate diagnosis, right? Without those reports, the doctor might just have to guess based on general knowledge, which in the AI world means hallucinating an answer. So, the LLM is the doctor, your private proprietary documents are the medical reports. RAG is simply the system that fetches those specific reports and hands them directly to the doctor. Grounding the AI in your private data provides the ultimate advantage: factual accuracy and user trust, virtually eliminating those dangerous AI hallucinations.
Let's move to Section 2, core architecture, and see how this builds out in practice.
Every working RAG pipeline relies on this standard data flow, and it's super vital to understand exactly how these pieces fit together. First, you ingest your documents and break them down into smaller pieces. We call this chunking, and we have to do it because LLMs have strict limits on how much text they can process at once. Second, you pass those chunks through an embedding model. This basically translates human text into arrays of numbers or vectors. To put it simply, it maps words into a massive multi-dimensional space where similar concepts live physically close together. Third, when a user actually asks a question, you embed that question into numbers too and perform a similarity search in your database to retrieve the chunks closest to the question. Finally, you augment your prompt with those retrieved text chunks and pass the whole thing to the LLM to generate a factual, grounded answer.
Now, you are absolutely spoiled for choice when building these components. Developers have this incredible menu to piece together their architecture. For vector databases, you might go with a dedicated DB like Chroma or Pinecone, but actually, if your application already runs on PostgreSQL, choosing an extension like pgvector might make vastly more sense for your specific infrastructure. Then you have orchestration frameworks, stuff like LangChain and Llama Index, to wire the database and the LLM together. And crucially, you need observability tools like LangFuse or Phoenix. Observability is essentially X-ray vision for your app. It tracks exactly which document chunks the LLM looked at, allowing you to instantly debug why the model might have given a bad answer.
All right, moving right along to Section 3, local setup.
Building a prototype on your local machine is remarkably straightforward today. You initialize a virtual environment, and using a fast package manager like UV saves you significant time right out of the gate. You securely load your API keys for OpenAI or Anthropic. You use a document loader to read your PDFs, applying a recursive text splitter to chunk the data. Now, a quick pro tip on this. Keeping your chunks at a sweet spot, say 500 to 1,000 tokens, is totally crucial because it generally keeps an entire paragraph whole without losing its surrounding context. Then, you embed and persist those chunks to a local vector store, wrap it all up in a prompt template and a retriever chain, and boom. You have a working RAG app right on your laptop.
And when you test it locally, it literally feels like pure magic. But Here is the harsh reality, and the biggest disadvantage of this basic setup. Local prototypes work beautifully for 10 carefully selected documents, but they completely, utterly break down at 10,000 documents. I mean, imagine the pain of seeing a prototype perfectly summarize 10 of your PDFs, but the second you hook it up to your company's entire massive Google Drive, the AI just completely loses its mind. That basic setup we just covered is exactly why we see a 90% failure rate in the real world.
Which brings us perfectly to Section 4, the production cliff.
So the crucial point is, why? Why does a system that answers flawlessly with a small dataset suddenly start spewing out garbage, returning totally irrelevant facts, or just hallucinating wildly when exposed to an enterprise-scale database?
And this brilliantly illustrates exactly why. The breakdown happens across 5 specific failure modes. First up, bad chunking. If your fixed-size chunker slices a crucial sentence right down the middle, you completely destroy the context. Second, embedding mismatches. Say a user asks, "How do I cancel?" but your documents use the phrase termination policy. That causes semantic drift, and the system totally misses the match. Third, retrieval noise. If a user searches for Apple, the tech company, but your massive database retrieves 8 documents about fruit orchards, the LLM is just completely confused by the noise. Fourth, context overflow. Stuffing too many retrieved documents into the prompt means the model often just forgets or ignores the data buried in the middle. And fifth, plain old hallucination, where the model gets overwhelmed, decides to ignore the retrieved context altogether, and just makes something up on the spot.
So, how do we fix it? That's Section 5, Advanced Architectures.
To survive the production cliff, we have to evolve way past the naive chunk and pray method. The first massive upgrade is Agentic RAG. See, traditional RAG is a static, one-way pipeline. Agentic RAG turns this into an autonomous, self-correcting brain. Imagine a user asks your bot for 2023 Q3 revenue. The agent searches but accidentally pulls the Q2 report. Instead of just blindly passing that wrong data to the user, an evaluator agent realizes the error, literally flags it as bad, rewrites the search query to strictly specify Q3, and searches again. It loops and self-corrects until it finds the exact right data. It's a total game changer.
Next up is Graph RAG. Standard vector search retrieves isolated chunks of data based on keyword or semantic similarity. But what if your question requires actually connecting the dots? Say a user asks, "Who are the competitors of the companies that John advises?" Standard RAG fails miserably here. But Graph RAG uses knowledge graphs to map entities and their relationships, acting way less like a keyword matcher and more like a detective string board. It inherently knows John advises Tech Corp, and it knows Tech Corp competes with Data Inc. It traverses these relationship edges to perform complex, multi-hop reasoning across your entire document base.
Then we have multimodal RAG. Let's be real for a second. Naive text extraction absolutely wrecks the formatting of nested charts and complex layouts. If you're a legal team analyzing contracts or a hospital scanning medical records, traditional text extractors just fail. Multimodal RAG solves this by using vision language models, like the Local architecture, to literally see the document. It converts the PDF page into an image and embeds the visual representation. This preserves the layout context perfectly, ensuring your system can accurately read a medical scan, a complex financial ledger, or a schematic diagram just by looking at it.
We also have to talk about contextual retrieval. Imagine you have a document chunk that just says, revenue is up 10%. By itself, floating in a massive database, that is entirely useless. But if you prepend a summary to that chunk saying Apple Inc. Q4 2023 financial report, suddenly that exact same chunk is hyper-relevant. Simply having an LLM write a document-level summary and attaching it to every single chunk before you embed it ensures the chunk never loses its overall meaning. Doing this one simple architectural tweak reduces retrieval failures by a staggering 67%.
Finally, let's look at Section 6, RAG versus long context.
This brings us to a massive ongoing debate in the AI community. With modern LLMs supporting literally millions of tokens in a single prompt, do we even need RAG anymore? Well, the short answer is absolutely yes. They are simply different tools for different use cases. Look, long context models are fantastic if a developer is uploading a single static codebase to analyze all at once. But what if you have an app with 10,000 daily active users querying a massive, constantly changing company database? Dumping 1 million tokens into a prompt for every single user request results in extremely high latency, and it is brutally expensive. RAG, conversely, offers unlimited scaling and is incredibly fast. Now, what's really interesting about this slide is the financial side, because the difference here is staggering.
Simulations run on real enterprise workloads reveal that a well-optimized RAG system can be over 1,200 times cheaper than constantly dumping your entire data payload into a long context model. 1,200 times. When you're building a production app, unit economics dictate everything. That massive cost reduction is literally the difference between a highly profitable scalable startup and completely running out of funding.
So let's add some color to these undeniable advantages. RAG is your absolute best friend when dealing with large knowledge bases over 100,000 tokens. It is essential for dynamic, frequently updated content because, you only have to update the new vector chunks instead of reprocessing a massive context window every single time. It's mandatory for cost-sensitive applications, and perhaps most importantly, it is non-negotiable for workloads that require precise source tracking. If you're building for healthcare, finance, or law, and the AI cannot point to the exact paragraph it used for an answer so a human can verify it, the business legally cannot use it. RAG provides that exact, precise citation.
We have journeyed all the way from those fragile local scripts that completely break at scale straight through the production cliff and into the cutting-edge agentic and graph systems of the future. The bottom line is this: the naive, basic chunk-and-pray strategy is officially dead. To survive in production, you absolutely need intelligent, self-correcting, context-aware architectures. But the good news? You have the blueprint now. You deeply understand the failure modes, and you know exactly how to engineer past them. So the only question left is, are you ready to go out there and actually build the future of RAG? Thank you so much for joining me on this explainer. Keep building, and I'll catch you next time.